Welcome to the course on computer design of electrical machines. We'll have a lecture 18 today on the design of single phase induction machines, part 3. We'll have a content for today's presentation starting from introduction, then design of workflow of single phase induction motor design, then motor network calculator named as Monica, and then YCA program for personal and mainframe computers, finite element design of single phase induction motors, and then optimized design of single phase induction motor, then algorithms for optimum design with the new concept of design of experiment and the response surface methodology, then exercises and references like. So starting from introduction, the digital computers have literally revolutionized the process of designing rotating electrical machinery, and more precise calculations are now being made on electrical machines with more accurate result, resulting in economical use of material and less testing and rebuilding. The computers can be used in many different ways to eliminate routine calculations by the engineer and to make the design process a science rather than an art. So the computers may be employed merely as a high-speed calculator and make a straightforward performance calculation on a fixed design. We call it the process analysis. Or the machine may in addition be instructed to select the certain physical variables which produce a desired performance, process known as synthesis. So the degree to which the second course can be taken depends upon many factors, among these being the power of the computer, the ingenuity of the group developing the procedure, and the amount of time allotted to the development of the program. So why personal computer or computer design is required? The personal calculation on single phase induction motors require 2 to 4 times as much time as comparable calculation of polyphase motors, and the repetitive calculation of design sheet is a cumbersome and never ending task. So the optimal design can never be reached with manual design calculation, and these are typically, as an example, the performance calculation sheet for single phase induction motor. As you can see, the number of formula for single phase induction motor, another sheet of the formulas. So there are plenty of formula you can just see. Here as a typically the 42 formula is given here for the just performance calculation of single phase induction motor, which is reported as a courtesy of from this typically from this research paper. Now coming to the why typically for the analysis part of analysis based design approach, the equivalent circuit of single phase induction motor is analyzed using the set of sequential instructions evaluated by computer and the choice of parameters taken by the designer. So moreover, the desired performance is based on experience of the designer, and this gives the advantage in estimating the performance of motor in a very short time space as compared to the iterative design sheet preparation. Now the another approach of the design, which we call it like a synthesis approach for computer design of these single phase induction motors. So designer is usually given certain performance specification consisting of such items as breakdown or log rotor torque, log rotor current, specification like efficiency, power factor and maximum temperature rise, etc. And the objective is to meet these with a minimum of material, labor and engine time and tooling cost. The usual design procedure of synthesis consists of following steps: establish the specification for the desired performance, estimate a design usually from previous experience, reference, institution or even ignorance, and make design analysis calculation consisting of density, losses, circuit constant, etc., and calculate the performance from these circuit constant, which may be constant or variable. Then the next step is like analysis of design. This consists of in comparing result of the design analysis calculation with the desired specification, also considering them in the light of the cost and determining what design changes are needed to make the design better, fulfill all the objective of performance and minimum cost or minimum weight as the case may be. So from the results, a new design or changes in the old design are prepared, and step 3 and 4 are repeated until the designer is satisfied or until the efforts appear to him to be will not be worthwhile. So now coming to design workflow of single phase induction motor design. So before understanding the computer aspect of design, the design needs to break down the design process into multiple subparts, and these parts could be referred as a subroutine and can be solved independently or in the main design workflow. In the following sections details a few of these subroutines involved in the design of single phase induction motor, which can be further used in computer design process. Like this is the design workflow is the start. Then we go to sub process 1, which consists of subroutine 1 or 2, or maybe sub process 2, which again consists of subroutine 1 or 2. Then we go to the decision and then end. So design workflow involving the sub process and subroutine. Now the typical examples is performance calculation sub process involving subroutine BS curve definition. So due to the design process being long and complicated with the many decisive parameters involved, it is usually preferred to be solved in parts or sub-process as shown. An example of pre-designed sub-process are given here as example. For example, start A, the process A, example of performance calculation, then subroutine A, then decision, and if it is yes, then and, or otherwise it go to like a example is BH curve characteristic as well as loss kg characteristic of the ferromagnetic material which are used in the design of machine, and then ends the subroutine. Now before starting the design process, the scope of design needs to be assessed. So what are the parameters like for example variables the designer had to have the flexibility to change or choose, and what constraint either design standards, client requirement or specific application requirement need to be considered. Can the design be optimized? If then, what are the objectives to be considered? So here typical example of his scope of design is like typically first we take a specification like power in watt or kilowatt, operating voltage and starting current, then frequency 50 Hz or 60 Hz, and rated maximum speed and torque, operating efficiency, duty cycle, number of phases, typical here single phase, starting method like capacitor start, shaded pole start, capacitor run, capacitor start, etc. And stator winding, main and auxiliary winding turns and gauge, and rotor winding turns and gauge, then air gap dimensions, voltage limit per winding and current limit per winding. Then the insulation requirement, winding layer insulation between windings and slot insulation, and type of windings, the winding type and sequence, typically integral, fractional or concentrated. Then the enclosure or frame type of coupling, shaft design, magnetic or non-magnetic shaft, type of footings, ambient temperature and temperature rise, and value within the limit. Then the 20th is stamping dimensions and thickness like starting from 0.2 mm to 0.6 mm, and 21 like a stacked material like M series steel, cobalt steel, etc. 22 is like a bar material, copper or aluminum, like a type of die cast like aluminum, copper or aluminum copper alloy. Then the 23 like plug density, designer choice or computer selection, typically of rotor, core and slot, and stereo core slot and air gap. Then modes of design, a computer design by synthesis or automated mode, or manual design like analysis method. Then size directed design like hybrid method. So the variables for typically for induction motor design could be the machine dimensions like stator, air gap and rotor, material choice, selection of average flux density like B average, air gap, stator slot and core, and similarly your rotor slot and core, selection of electrical loading small AC, type of winding and turns, stator and rotor skew angle theta linked to the resistance, and stack land to pole pitch ratio L upon tau, and current density selection also linked to ventilation and cooling. Like so this, then the 9 capacitors value selection as per type of single phase induction motor like starting performance, like it affects the starting performance, then ending dimension, depth of the width ratio, and cooling and ventilation. So these are some of the variables which can be considered. Like then the objective function for this, synthesis or design optimization problem. The objective functions for induction motor design could be minimize overall cost, including the cost of material, labor, and losses, maximize efficiency like power output, etc. Could be single objective or multiple objective with proper weighting constraint. And constraints are the for induction motor design will be resistance and leakage, possibility flux density of that material, saturation limit, physical dimension of machines like winding, and induction motor design of course is a constraint design problem. Now coming to sequential steps for design of each part of the single phase induction motor. Calculate the main dimensions of stator core outer diameter, width of the tooth, stator core depth, slot width and depth, air gap length, then calculate for the main winding number of turns in each coil, conductor diameter by checking current density, calculation mean length, resistance and copper losses. Then calculate the rotor diameter, number of rotor slots, conductor diameter, core depth, resistance and copper loss, and weight of the rotor copper. Calculate the Carter coefficient for ampere turns for air gap, the stator tooth, the stator core, rotor teeth and rotor core, and no load ampere turns and magnetizing current. Then the fifth step, calculate the auxiliary winding, number of turns in each coil, conductor diameter by checking current density, calculation mean length, resistance and copper losses. And sixth step is the calculation of width of the tooth, core iron loss, total weight in typically kg per horsepower, and 7 is solution by equivalent circuit, slip versus torque curve. Then this is typically the example how the calculation according to the reference sum given for simplified flowchart for computer program. So the map shows how various program can pass data from one to another by the way of disk, and within the boxes are given very brief sketches of what each program does, as well as the nature of the data passed from one program to another or from one subroutine to another subroutine. I mean, as a total simplified flow chart of the typical design of latest material, cost of phase binding, and then typically flow chart for design of this complete induction motor. Then the flow chart for design of the stator is starting with the as a data, all input data, as a power rating, voltage, number of poles, frequency, speed, efficiency, power factor, average flux density and electrical loading, rotor speed, then calculate kVA, then calculate the output coefficient, then determine the synchronous speed, calculate D and L. If the peripheral speed is below 30 meters, if within the limit, then otherwise you have to change the specific electric loading and magnetic loading. If yes, and determine the stator slot dimension, design the main and auxiliary windings, determine the conductor size, calculate the total number of stator slot, stator conductor, design air gap length and print the value. This consists for design of stator. Similarly, calculation of main dimensions of process with the starting again from main data like power, frequency, synchronous speed, efficiency, power factor, magnetic loading, electrical loading, winding factor and stacking factor. So calculate the pole from 120 by P, then the aspect ratio L upon P equal to, and then small a C into pi by P, then D square L from output equation, then calculation of D from aspect ratio, and then calculate the L, and then calculate the Li from stacking with the number of ducts, and then stop. So this is about the calculation of main dimension. I mean, how we can use the computer for typically design process. So this is for stator design, typically starting from input voltage, connection type and stator winding factor, then the calculation of slot opening, then width of the teeth from formula stator depth, then the width of the slot at bottom, air gap estimation, winding factor calculation, flux per pole, turns calculation, main winding current, conductor area of main winding, mean turn length of the coil, and then length of the mean turn, resistance of main winding, and then typically calculation of auxiliary resistance calculation and end. So similarly for design of the rotor, starting from typically give the design specification, parameter and constraint, then find the main dimension DL and determine the air gap length and diameter. Then typically go to the perform selection of stator slot, study number of selectors and winding design, determine the number of your slot, rotor bar current and depth and rotor core, calculate the end ring current, determine the copper loss in the rotor bar and ring and current density, calculate the slip. If within the obtained, if it is not, modify the flux density and resistance. If yes, then find the temperature rise, and if theta is within limit, not, then change the conductor size, slot size and current density, or otherwise print the result like. And calculation of similarly rotor design sub process, starting from stator dimension D and L, and calculate the air gap length LG, then rotor diameter DR, then select the rotor slot S2, then calculate the B to T, then the bar cross section area, then depth of the core, rotor core, then the bar length, then area of the end ring, the resistance of the typically of the rotor referred to stator, then the leakage reactance calculation referred to the stator, then your total leakage reactance, and then the transfer this entire all leakage reactances, and then the typically calculate equivalent circuit and then stop. So now this was the all calculation how we can do use the computer for the calculation for different parts, either for design or equivalent. Now this is the special software made by Professor C.G. Winnett called motor network calculator. In short, they call it Monica. So this Monica, what it does, it is meant for single phase motor, comprise the large majority of electric motor being made today, and curiously enough performance calculation on them are more involved and more time consuming than the similar calculation polyphase motor. So on the running connection, for example, it takes at least twice as long as calculate to single point as it does for a polyphase motor. On the starting connection, it takes at least 4 times as long, and as a consequence, many calculations that should be performed are left undone. So an analog type of computer was felt to be better suited for this application than digital for a number of reasons, and reproducing the circuit for a motor direct on network calculator affords the engineer operator an excellent picture of the what happening. And moreover, if one wishes to change the value of one or more constant, they can observe the effect of the change instantaneously. Hence, the analog type of undoubtedly faster and more investigation. So while accuracy is somewhat less than could be obtained with the digital computer, probably greater than the accuracy with the known, he or she know the constant. On accuracy with he or can test the completed model. So this is typical example, like how you can say, starting with the top of the left hand of the rotor panel, row of panels, the control for magnetizing reactance, primary winding rotor circuit action range of the rotor circuit analysis. The middle panel reads the top blank and future, bottom cage rotor circuit main winding, that GI metering control. Right hand panel is blank for future use, capacitor, auxiliary winding, and this. So this is virtually typically as a outcome of a research paper by Professor Winnett for the single phase induction motor design. And detailed schematic diagram is reproduced in previous figure, which is mounted on the calculator just in the right of the operator flagship window, and it is great assistant in a OI operator in helping one of know which switches to throw or to grab the significance reading more readily. And one of the set of electronics low loss meters is used in all readings. Circuit themselves are located to remove panel above the operator, and this control knobs are on panel. 2 voltage sources are provided. Voltage and phase of these can be controlled independently. So leads from all the circuits and voltage sources are brought out to connection panel and below the extension lead, and the instruments are connected to any design circuit by means of switches located on sloping panel between the schematic circuit and the meters themselves. And to the left of the instruments are meter current control switches. These select any one of the 3 voltage scales and one of the 5 current scale. They also control wattmeter polarity and like the permit use of the wattmeter to read the watts or VR, either amperes or volt in vector form, giving an answer either in rectangular polar coordinate, and extension leaf ordered to the operator right to support his data sheet and when recording readings. All dials and control except those for magnetizing reactance can be reached by the operator while sitting on his chair. So since the magnetizing reactance is seldom changed in course of the motor performance calculation, most calculation can be performed and recorded by the operator without him moving from his chair. All circuits are numbered and are identify or removable cards on the panels when they are located, and these identification numbers appears as a schematic diagram reproducing subsequent one right opposite to the circuit selector switch. And this is typically how the typical circuit here given for schematic diagram calculation for revolving field, and all the calculated data from this Monica software data sheet for a single phase induction motor and capacitor motor of half HP, 115 volt, 6 pole and 60 Hz. Then the speed torque characteristic of typical half horsepower capacitor start motor plotted from the data of table. Then the speed torque and power input curve for permanent split capacitor with single phase and double cage rotor computed by calculator. Now there is another software which are converted from this called VICA program. So VICA is pronounced V, who is a acronym for Winnett Interactive Computer Aid, and VICA program developed by Dr. C.G. Winnett are a set of general purpose computer programs used in a nonlinear magnetic design of the AC induction motor, and the original programs were written in scientific programming language called Photon. So map shows how various programs can pass data from one to another the way on the disk. So with this of course going to Wi-Fi is on digital computer programs in Photon. So boxes are given to very brief sketches of each program does as well as nature of the data pass from one program to another. So it's a map of typically system of Wi-Fi program interactive computer design of single phase induction motor according to typically from this reference. And this is another, I mean you can call it flow chart of the winding design from this reference given here. So now coming to these are the of course the computer used using analog and digital for the design of single phase induction motor and winding design. Now I mean nowadays we are using of course finite element design for single phase induction motor, especially for very low rating where these all empirical relation does not work properly. Now the typically is a multi-physics computer design approach for single phase induction motor starting from stage 1 like a design requirement, then stage 2 performance, then stage 3 cooling, stage 4 manufacturability, and of course you consider template spreadsheet for performance, it's electromagnetic and thermal performance, and then of course structural as manufacturability. So this is here is the fundamental elements of single phase 3D FEM model of the investigative single phase motor, slightly rotor view, front view of the winding and side view of the 3D FD single phase motor, and which is reported in this publication like as a design of single phase. And these are the typically simulated performance of the single phase motor which is designed by using finite element analysis. So coming to now as a combination of finite element and analytical based design. So finite element is used to estimate the 2D parameters of the motor, where the 3D ones are commercially computed analytically. Then the induction motor performance is predicted from the settled equivalent circuit, and fast prediction of the induction motor capability compare rapidly various configurations with reasonable accuracy is desired. In a practical design of induction motor, commercial laminations are adopted and the geometry of lamination is fixed, where the design variables remain the motor stack length and the number of turns per phase. So this is typically a scheme of combined finite element analytical procedure which start from motor data, then we go finite element analysis to for typically calculation of no load and log rotor and working verification, and then of course analytically we calculate it typically the equivalent circuit, then performance computation with the equivalent circuit from 3D calculation and the performance calculation, then verification from the result like. Then there is a of course computer used for thermal analysis of single phase induction motor. So thermal network analysis can be subdivided into two main calculation types. So heat transfer analysis is the thermal counterpart to electrical network analysis with the following equivalences: temperature to the voltage, power to serve current, and the thermal resistance to electrical resistance. And flow network analysis is it is the fluid mechanics counterpart to electrical network analysis with the following equivalences: pressure to voltage, volume flow rate to current, and flow resistance to electrical resistance. So in the heat transfer network, a thermal resistance circuit describes the main parts of the power flow, enabling the temperature of the main component within the machine to be predicted for a given loss distribution. In the thermal network model, it is possible to lump together components that have similar temperature and represent each as a single node in the network, and nodes are separated by thermal resistance that represent the heat transfer between the components. So inside the machine, a set of conduction thermal resistances represent the main heat transfer path, such as from the winding copper to stator tooth and back iron, from the tooth and stator iron nodes to the stator board and housing interface. In addition, the internal convection and radiation resistances are used for the heat transfer across the air gap and from the end windings to the end caps and housing, and external convection and radiation resistances are used for heat transfer from the outside of the machine to the ambient. So unlike the three-phase motor, the single-phase motor does not exhibit winding symmetry and consequently different temperature in the different parts of the machine. Thus, the prediction of an average winding temperature only is not enough. For accurate analysis, two strategies could be applied mainly: the analysis by means of finite element analysis or by means of involved thermal network, including circumferential heat flow component. And however, both strategies require complex models and considerable pre-processing and solving time. So the equivalent circuit thermal network is based on the lump parameter network that is solved by 2 times, each of them using equivalent copper losses and as heat loss sources. And the procedure presents 3 main advantages. Firstly, it allows the 2 different winding temperatures rises to be computed separately, transient and steady state. 2. As second advantage, the lumped parameter network is the same as symmetrical 3-phase motor, simply solved more times. So therefore, it is not difficult task to adopt the thermal analysis procedures commonly used for three-phase motor to the single-phase one. And finally, this analysis technique is very rapid because it allows the different temperature ranges to be computed without using finite element traces or more complicated network, such as those considered circumferential heat flows. And typical example is a thermal network, the cylindrical representing the each motor component and thermal network and overall motor thermal network. You can just see how with the thermal and how the thermal equivalent circuit with different regions are given here, with the even including the equivalent circuit of the capacitance which emissivity of the temperature. And this is the again the example of heat transfer network for this electric single phase induction motor like and this is typically a, you can call it the thermal analysis data on computer from this for typically the rise for the temperature also. So coming to like finite element method for thermal analysis, finite element analysis is now a standard tool of electromagnetic analysis. Both 2D and 3D models are used. Often software package for electromagnetic analysis also include a module for thermal analysis. At first glance, FEA seems more accurate than the thermal network analysis. However, it does suffer from the same problem previously described with the uncertainty in the computation of thermal resistance due to interface and convection. The main role of FEA is in the accurate calculation of conduction heat transfer in complex geometry shapes such as heat transfer through strands of copper in a slot. And for this problem, FEA analysis can be used to calculate the equivalent thermal conductivity that can then be used in network analysis. So this is finite element method for thermal analysis. So you can say steady state to FD element analysis of temperature rise in a slot with the rectangular copper conductors. And so you can say how thermal analysis using computational fluid dynamics. So CFD applied to the design of electrical machine primarily aims to determine the cooling flow rate, velocity and pressure distribution in the cooling passes or around the machine and the level of surface heat transfer for subsequent analysis of temperature in the active material and remaining solid structure. This method can replace the combination of traditional one-dimension ventilation resistance network based on the correlation for pressure drop across local and frictional resistances and correlation for surface heat transfer coefficient. They typically model of the fluid flow around the end winding of using NSS fluid. Then the types of CFD analysis for electrical machine can be divided into two parts. A, in internal flow, either in a through ventilated machines where the ventilation is driven by a fan or self pumping effect of rotor, or in a totally closed fan cooled motor generator to assess the air movement that exchange heat with the winding overhangs to frame. And B, the external flow and flow around the enclosure of a TFC motor generator. The C is fan design and performance study. Due to cost of material, manufacturing process, space or accessory constraint, fan employed in the electrical machines often have very poor aerodynamic efficiency. So in that case of radial fan, there are rarely any means of pressure recovery at exit. So CFD offers a great deal of help in improving the fan design and its interaction with the cooling circuit. And D, supporting analysis, the water flow in the cooling jackets, cooling of associated power electronics. Now coming to optimal design of single phase induction motor or design optimization of single phase induction motor. Optimization of single phase induction motor. The optimized design of electrical machines is a non-real multi-objective problem. In electrical machine design, the objective of such as highest efficiency, lower cost and minimum weight of active material have to be simultaneously met. So further, this electromagnetic problem should be solved with consideration of the mechanical, thermal and material constraint. And the results of such multi-objective optimization problem are interrelated with the use of Pareto fronts. Pareto front is a geometrical entity along which the improvement in objective can only be achieved through iteration in another objective. So the Pareto front can aid in identifying a family of the best design. So it also provides a fair basis for the comparison of different machines topology, and comparison at only one design point might lead to erroneous calculations. And this is typically the Pareto front diagram shows material cost and Pareto front and the fluid typically fundamental power factor along with the Stochastic loss with respect to that. So Pareto in a front objective and finite elements is used for the performance calculation. So the step in the process of formulating optimization problem are identification of objective function, selection of input design variables and definition of the constraints. Like you can call it single weighted objective function formulated for n performance indices as follows: f0 equal to n small n equal to 1 and W1 Fn as a function of x, where W1, W2 are the weights, and the advantage of such a method are simple implementation and interpretation of result as compared to multi-objective optimization. However, correct choice of the weight is really a challenge here. So now coming to multi-objective optimization. So rather using a single objective function combining all performance indices, individual objective function corresponding to each performance index are defined, and the advantages are that no weights are needed, and a family of the best compromise design can be identified from a Pareto plot. The limitations of this approach are that the implementation is more complex and the results might be hard to interpret. Examples of multi-objective functions that could be used in electrical machine design are torque per unit mass, torque ripple, etc. For example, Ft equal to Tm upon Wpm, where F ripple equal to maximum Tm minus minimum Tm divided by Tem. So now the objective function is defined by the designer for satisfactory performance in certain bound. That for an example, an aggregate cost, that is Ct, that contains the initial cost Ci, loss energy cost Ce, and the penalty cost Cst applied to the motor start ability requirement are not met. If the mechanical output power Pmax is less than the P rated power Pn, the initial cost is multiplied by over unity factor Pn upon Pmax as follows. So Ct equal to Ci into max of 1 comma Pn upon Pmax plus C plus Cst, and the initial cost contains the material cost C mod and capacitor cost. So Ci equal to C mod plus Cc, and the motor cost is computed as the active material cost by multiplying the active material weight and the unit cost, copper stator laminations and rotor laminations, rotor cage and frame cost, estimated direct ratio with the total active material cost, and the capacitor's cost is estimated considering the linear dependence on capacitor cost with their values through a KPC proportional coefficient cost and the offset cost. So Cc equal to C0 plus KPC in bracket Cr plus Cs, where Cr is the running capacitor, Cs is the starting capacitor, and the energy cost is based on energy price, motor efficiency, and on lifetime in numbers of years Ny and average hours per year Nhy. So Ce equal to Pn in bracket 1 upon eta n minus 1 and dot multiplied Nhy Ny divided by 1000. So now coming to steps in systematic design. First is establishing the specifications. The second is selection of motor topology. Third is initial sizing based on analytical calculation. Fourth is optimal design including electromagnetic, mechanical, and thermal constant, including the estimation of performance and the cost, and while studying the sensitivity to manufacturing. Then these two major approaches for automated design optimization, as a combination between the two are possible as the machine specification and decision design. One process is design of experiment called DO in short, with the parameter correlation and response surface RS and estimated performance and based on RS, and then Six Sigma analysis. And the advantage is familiar engineering background, include indications and input output correlation and sensitivity analysis. And then the typically computational intelligence, the difference evaluation, other like GAPSO, etc., and inspired from natural selection and generation oblique population of each with multiple examples. And then advantages is the minimal computational effort for large scale optimization study, thousands of candidate design, and of course this with the cost versus performance characteristic for the best design. Then the selection of optimization technique. So there is a classical optimization technique which used for solving this problem, not only modification. So solution technique is the problem dependent. If the linear programming method model, use the simplex method. If integer programming model, then use the branch and bound. And then if it's a general purpose solution technique, is use the genetic algorithm, simulator annealing and uncolonial optimization, or artificial B algorithm, and of course AG problem, then nature inspired heuristic optimization technique. So this is typically the classification, the different optimization technique. So as a case study, coming to like a optimal design of single phase induction motor, the optimal design of motor dimensions, the capacitance of the run capacitor, the winding distribution, and the choice of electrical steel are the most important sources for improvement of the efficiency of the modern single phase induction motors for given performance and material cost constraint. The formulation of the technique which realizes the optimization is dealt based on the nonlinear programming approaches. So a comparative study for both the method of bound search along active constraint and the Hen-Powell method is performed from the theoretical convergence and practical application point of view in order to develop the best method for optimization of single phase induction motor design. So coming to the first optimization component is usually formulated as general nonlinear programming minimize the f as a function of x such that s as a variable exists. The n-dimensional feasible design T and x belongs to D, where the D is the space with the x variable and x greater than 0, and the constraint Gi is less than or equal to 0, where I equal to 1 to 3 up to m. So then in the above equations, f, x, gx are the real valued scalar functions, and the vector m comprise the n principal variables for which the optimization to perform. The function f is called the objective function, for which the optimal values of x result in maximum of the effect, and these optimal values satisfy the given constraint. The objective function may be identified with eta, which is the efficiency with a minus sign in front. So minus sign means the maximum efficiency is required, and Cm, which is the material cost, including the cost of capacity of the motor. So in typically inequality constraint Gix less than 0 include the performance property of the motor, dimensions, restrictions, and additional requirement of customer. Note that every constraint can be written as Gix less than equal to 0, since any constraint in the form of Gi greater than can be changed to above standard form by introducing a minus sign before the constraint function. So in the feasible design region D, the every x design given the constraint. So the mathematical model for optimization of the binding distribution is also can be as follows: maximize the eta as a function of x such that the minimum SL and M13 is less than 0.3, where eta is the efficiency. The motor STL is the copper losses section of the fuel stator slot. M3 is the ratio between the third and the first harmonics of the magnum MMF of the entire stator winding. So now coming to the following design quantity are chosen as a principal variable in optimization, like a stator x1 as a stator border, x2 as a stator core line, x3 number of turns in a series of main winding, x4 as a number of turns in series of auxiliary winding, x5 wire diameter of main phase winding, and x6 is a wire diameter of auxiliary phase winding, x7 average rotor slot width, x8 is stator slot height, and x9 rotor slot height, and x10 is a stator yoke height. And the performance constraint Gi for the single phase induction motor can be power factor at rated load should be greater than 0.724, log rotor current to be greater than log rotor to be as a greater ratio that ILR less than 6 per unit, and starting torque to rated torque as a 2.3 greater than 2.39, and back down torque to rated torque should be greater than 1.8 per unit, and temperature rise according to the insulation U at greater less than 65 degrees Celsius, and slip should be rated less than 3%, and the material cost except cost of capacitor will be around $120 for a specific problem. This is typically the example forms this reference for the complete design calculation, as it is mentioned the procedure like efficiency contribution and optimization process with the 12 microfarad and 50 microfarad as a material cost of, and similarly efficiency this for typically for capacitance and run capacitance, then the efficiency material cost. So these are the typical data for a particular case of optimization of single phase induction motor with maximum efficiency and minimum cost of design. From this reference to efficiency material cost and order constraint in plane. Then the efficiency and power factor relation for 3 represented electrical steels. Then the increase the efficiency due to the optimization of the winding distribution as a function of capacitance and value of run capacitor. Then the increase the efficiency as a function of capacitance to run. Then the efficiency and power factor as a function of load for the optimal and original design of 2 horsepower machine rated with run capacitor capacitance value with the 12, 50 and 93 microfarad with their metal cost except of capacitor as a $120. So this is about a typical example case. Now coming as a procedure of design of experiment, DOE. In short, in brief, it's called quite popular technique nowadays, which reduces the number of calculations, and we go in a particular precise manner for the calculation. Otherwise, there are large number of the design calculation to be done. So in this design of experiment, in a process of engineering design, it is very important to understand what and how any input variable are contributing factor to the output parameters of interest, and it is a lengthy process before a conclusion can be made as to which input variable play a role in influencing the output parameter, and design experiment help revolutionize the lengthy process of costly and time-consuming trial and error search to a powerful and cost-effective statistical method. So, design of experiment in short is called DOE, and response surface method RSM methods and technique which are employed for the establishment of a relationship between the input and output of a system. This relation could be used for optimization. So, in case of any an electrical machine, the designer is interested in the performance, say reduction of torque and cost and improvement of efficiency. The typical example is here general method of process system with the uncontrolled factor as input and control factor and output. So, the performance are defined as responses which are functions of independent geometry variables. For example, air gap, stator tooth width and total pole arc, and the independent geometry variables are input design variables constitute the input, and the relation between the responses y and the input design variable x can be established by a series of experiments. That is a general method of process of this system. So, there are several versions of design of experiment available in engineering literature. So, these techniques all have one common characteristic: they try to locate the sampling point such that the space of random input parameters is explored in the most efficient way, or obtain the required information with the minimum of sampling points. And sample points in efficient location will not only reduce the required number of sample points, but also increase the accuracy of the response surface that is derived from the results of sampling points. So, the design of experiment is a process of planning experiment in a systematic way so that data collected can be used to fit appropriate model. And prior to conducting the experiment, the levels are defined for the input design variable, and full factorial design refer to the series of experiments where the value of the input design variables are fixed at a procedural level, predetermined level. And for instance, in a two-factor full factorial design, the independent variables a and b, the runs are as in table on the next slide. So, the data from the experiment can be analyzed with the help of main and interactive effects. So, you can just see here how it is like a run with the A, B, and then the run for 1 to 8 as considering the typically. So, table 1 runs in the 2-level full factorial design. Plus and minus refer to the minimum and maximum values of the input design variables, namely. So, you get a 4 combination with the 2 variables. The run in 2-level 3-factor full factorial design with the it comes with the typically 9 combination with the A, B, C 3 variables, and you come with the combination A, B, B, C, C as a factorial and as A, B, C. So, you virtually get like typically the 8 combination from this like. So, coming to fractional factorial method. So, for systematic where a large number of input variables are expected to affect the output, the number of full factorial runs becomes the prohibitively high. So, this is when the fractional factorial method can be used. So, previous table shows the runs required for a 3-factor 2-level DOE. A total of 8 runs are needed to estimate all the main and interaction effect. So, coming to like a fractional factorial method, the main effect A is equal to 1 by 8 in bracket minus y1 plus y2 minus y3 plus y4 minus y5 plus y6 minus y7 and plus y8. The interaction B similarly, interaction effect of AB equal to 1 upon 8 y1 minus y2 minus y3 plus y4 plus y5 plus minus y7, y6 minus y7 plus y8. And interaction ABC is equal to 1 upon 8 minus y1 plus y2 plus y3 minus y5 plus minus y4 plus y5 minus y6 minus y7 plus y8, where y1, y2 represent the outputs of the run 1 to 8. So, now to come a point to be noted in that the signs of AB, ABC, etc., which are the sign of the coefficient in equation, are also obtained by multiplying the signs of the appropriate A, B, and C column. In case one wants to do a half factorial run for this segment, it will mean relation of 4 rows. Like. So, as an example, consider only the second, third, and fifth and 8 runs of the table, and in that case, you will have a main and interacting effect as a rewritten A equal to 1 by 4 y2 minus y3 plus minus y5 plus y8. Similarly, you have ABC and all the typically going up to ABC. You have to define all typically effect of all A design. So, thus A equal to BC, B equal to AC, and C equal to AB which means it's not possible to distinguish between these effects. In other words, the main effects are confounded with second order interaction in a factorial run, and domain knowledge. Typically, electrical machine expertise will help one identify which is the input variable is likely to have significant effect on the output, as well as the highest order of interaction that need to be considered, and accordingly the decision whether to run fractional factorial or not to be could be taken. Now coming to design of experiment about by Taguchi orthogonal arrays. So Taguchi orthogonal arrays is another method of DOE. So there are options for creating Taguchi arrays for the design of experiment depending on the how many times one choose to test each level of each parameter. For example, consider an experiment with the 3 parameters and 3 level of each parameter, p equal to 3 and l equal to 3, as discussed in previous learning module. So one shows that 2 Taguchi array for this case is a 6 run array for testing each level of each parameter twice, and 9 run array for testing each level for each parameter 3 times. So the 9 run array is more desirable if the cost and time permit, because each level of any one parameter and all the 3 level of the other parameter are tested. Of course, either array here costs less to run than the full factorial analysis, since the number of required runs for a full factorial analysis is equal to n equal to LP. So one can call a Taguchi array or orthogonal array. Some author call it as a full orthogonal array when for each level of particular parameter, all L levels of each of the p minus 1 other parameters are tested at least once, and sometimes as p increases, it is necessary to test all level of the parameters more than once in order to meet the rules for Taguchi array as discussed previously, and in such cases there should be no unnecessary repeats. So for example, consider that p equal to 4, l equal to 3 case on the next slide, when the parameters is a is at the level 1, parameter b is tested at level 1 to 3 all levels, and similarly parameter cd are tested for level 1 to 3 all l levels, and the same things hold when parameter a is at 2 level or 3 level. So same things hold for all of the parameters. Hence we see that the definition of orthogonal array holds for this case of each level particular parameter, and all L levels for each of the p minus 1 other parameters are tested at least once, and only once in this particular case. The required number of runs is therefore 3, L equal to 3, and into 3 each level of each parameter tested 3 times, so equal to 9 required runs for each orthogonal array. So consider another example, typically with the p equal to 5 and L equal to 3 case on next slide. So when parameters A is level 1, B tested level 1 twice and level 2 twice and level 3 thrice. So thrice for all 3 levels. Similarly, parameters CD are tested twice at level 1, 2, 3 for all L levels, and the same things hold when parameter A is at level 2 and 3. So same thing holds for all of the parameters. Hence our definition of the orthogonal array and holds for this case for each level of a particular parameter, and all L levels of each of the p minus 1 other parameters are tested at least once, and actually twice in the particular case. The required number of runs is therefore 3, L equal to 3 level, and into 6, each level of each parameter tested 6 times, so equal to 18 required runs for this orthogonal array. The orthogonal array are the best and most common type of Taguchi array, and encourage to use orthogonal array whenever times and cost permit. Table of Taguchi orthogonal array is provided below for the value p equal to number of parameters ranging from 2 to 5 and L number of level ranging from 2 to 5. And this is a typically table with the 2 variables and 2 levels, where you have a typically p equal to 2 and L equal to 2 for the 3, 4. For p equal to 2, 3, 4, 5, it is shown here with the L equal to 2, then L equal to how really it goes with the 2 variables with 2 level, and 3 variables 2 level, and 4 variables 2 level, and 5 variables the 2 each level. So you just see how the Taguchi array formulated with the number of, typically you can call it the kind of array forms from this and similarly for 2 variables 3 level. So here all is the 3 levels, and how the array get formulated with the p equal to 2, 3, 4, 5 with the 2 only with the typically with the 3 levels and similarly with the 4 level, how the Taguchi array changes with the 2 variables, 3 variables, 4 variables, and 5 variables with the 4 level, and with the again with the 2 variables with the 5 levels, how this Taguchi array changes for 2 to 5. So now coming to a conclusion of this Taguchi orthogonal array, the experiment test array are usually chosen based on the compromise between the cost of experiment. Cost include the time required to run the experiment and the required accuracy of the result. Now below is the hierarchy how one should choose the test array. So for increasing the, of course, for increasing you should go full factorial. So starting from Taguchi non-orthogonal array, then you have an orthogonal array and full factorial array. So that is the increase accuracy, and of course it decreases the cost when you go to probably from full factorial to Taguchi orthogonal or Taguchi non-orthogonal array. Now coming to design experiment by response surface methodology is another technique in DOE. So response surface model, the relation between input and output of the system is given yn equal to fx is function of plus beta, and the input design variables are called natural variables if expressed in the natural unit of measurement, length in millimeter and angle in degree. The natural variables may be transformed in coded variables, dimensionless by definition with a mean of 0 and then same standard deviation such as C equal to C as a matrix of C, factor of C to CDV and equal to x minus in bracket x minimum plus x maximum by 2 divided by x max minus x minimum by 2. So function may be reformulated in terms of coded variables using a first or second order list model, y equal to b beta 0 plus summation of y equal to dv bi ci, then I equal to 1 to dv, then bi I ci I square plus then the further I equal to dv and then I j equal to I plus n dv bij ci and cj, where b0 bi bii bij are the regression coefficient, and the fitted model is called a response surface model called RSM, and second order RSM are widely used. A second order RSM for the two design variables is given here, like y equal to b0 plus b1 c1 plus b11 c1 square plus b12 c1 c2 plus b2 c2 plus b2 2 c2 square plus theta. So typically the evaluation of the main and interaction effect help determining the type of RSM that may be fit. If only the main effects are important, then the interaction term b beta 1 2 may be eliminated, and from previous knowledge, if the system is expected to be nonlinear, more than 2 levels are needed, and even in such system a 2 level DOE may be run in the initial scanning phase to determine the which variables would have an effect on the output. So the minimum number of experiment n required to determine first and second order coefficient of RSM is given here, n equal to 1 plus dv plus dv in bracket 1 plus dv by 2. So further, in order to fit a second order response surface, at least 3 levels of the input design parameters must be considered. This is typically the methodology of response surface method, how we go algorithm for DA for RS method, and examples of input variable index, and then example. So starting from, you define the problem of input output, then statistical scaling, then response surface, then approximate relation between the input and output through computational efficient model, and identify the optimum based data. Then of course what you get typically as a example of input and output, and then following as a response surface, how you plot it typically of your in 3 dimensions, a performance and parameters, in parameter 1 and 2 with the performances like as a 3 dimensions surface model. Now coming to optimal design, example 1 as a Taguchi orthogonal array. So optimal design example 1, a systematic approach starting from one existing single page of motor is presented for the improvement in the efficiency of motor in 2D finite element analysis, and Taguchi orthogonal array are used to improvement in the performance of the motor. So design parameters which can be played with stack are with the stack length of the motor, LST, and number of turns in main and auxiliary winding, and MNNA or capacitor, and the wire gauge is main auxiliary winding, GM and GL, and the ending height and ring width, and rotor bar area, and the rotor teeth. And from this research publication. So the first 2 stage uses L18 orthogonal array with 1 design variables and 2 levels, and 7 design variables and 7 variables, as you can see in the diagram. And Taguchi L18 matrix is especially chosen for this work, since the interaction between the design of variables is distributed in a quasi-uniform manner across the column in the matrix. And the first stage deals with the design of optimal design of, and the second stage deals with the rotary design variables. Like so, here it is shown how it goes to typically. So here it is a optimal design typically as a coded levels of the first LO18, starting 1 to 3 level, and the variables typically starting A, B, C, D up to H, as we mentioned, as the number of poles and the number of main turns, auxiliary turns, capacitor, of course is a capacitor and motor. So then stack length, the conductor called main winding conductor bar area, and typically the your auxiliary winding cross section area like. And similarly coded level for second OA, I mean with the level 1, 2, 3, then HE, height of winding, TR, cap, extra value A, B, W, E, L, NM and NA, and here coded typically, as you can see the probably complete geometry, the different parts of the motor in the cross section B which are shown here, the level 1 and 2 for the number of turns, auxiliary main, and the coded bar for the width of the teeth and the bar cross section area with the level of 1 and 2. So now you can see here the typically the arrangement of the levels coded 1, 2, 3 for design variables coded A, B, C, D, E, and H of each design, and response from finite element analysis for the first and second L18 OA are illustrated in the table, and the input to the finite element simulation are the geometry of each run, winding data, and the entering and ending parameters. Like as you can see here, the typically how really the efficiency, I mean really getting affected in case of your first L18 and second L18 like. And this is the typically the main effect of efficiency of control setting as the main effect of the first L18 OA, and the second typically as the control factors with the main effects of L18 OA. Then the optimal selection of level of A1 and B2 on L4 OA. Therefore, the number of turns in main winding auxiliary winding are selected 375 to 70, and the optimal variables evident from plots are A2, B3, C1, C2 on DL18 with the, again the efficiency with the control variable main effect of third L and main effect this. The comparison of old and new stator laminations, comparison of old rotor slot with new rotor slot. I mean you can see the laminations of old laminations and new lamination, how it is get modified, and then similarly with the new, with the old rotor to new rotor like. And then typically the kind of performance, the current main winding, auxiliary winding, and supply current, and the torque characteristic of load as well as the motor like. And then the typically the existing and prototype, how it is the changes. So power output with voltage, how it changes, and the power copper loss and main winding, auxiliary winding, how it changes with typically like. And then the with the existing and prototype, how it is changing typically the speed and power factor, then the your supply current and power output like with the speed. Now coming to design example 2, the magnetic equivalent circuit based model. So analytical method based on magnetic equivalent circuit is proposed to evaluate the performance of the motor. The influence of rotor slot is going, stator winding, and slot leakage, inductance, and the core saturation are included in the model. And the furthermore winding copper losses and the core iron losses are also calculated using the proposed model. And here you can see how really the finite element analysis gives the complete details of the flux density pattern in this with this matching. Magnetic flux lines, the distribution of magnetic flux density, and the schematic of matches on the studied single phase induction motor for the condition that prescribed in section 4B for the nonlinear core times 40 millisecond, that is inner outer carried 386 milliampere and 520 milliampere respectively, and the rotor bars conducted the internal current line. This is the proposed magnetic equivalent circuit for the stator and rotor core and the air gap. And then typically the schematic different parts of the single phase calculation of stator permeance, stator yoke permeance, permeance, of course to calculate the performance these parameters for magnetic equivalent circuit. The schematic different parts of single calculating stator permeance, yoke, and stator teeth permeance. Then the proposed equivalent circuit of single phase ignoring the leakage reactance of the end windings of the slots. Then typically block diagram of proposed model with the complete process, how it goes, input geometrical parameters starting with, and then finally going to be final design of this single phase induction motor like any steps from this reference. And then the electrical circuit of rotor and the stator, and then the comparing the results of proposed model with those of APM, considering the core with the speed of 350 rpm and supply voltage of 220, starting from current, voltage, power, and typically the current, and typically the different kind of current like. So now coming to design example 3, winding magnetization design. So a systematic stator winding design scheme that can effectively improve the operational efficiency of commercial single phase Western motor. without changing the circuit component and structural constraint. The motor stator winding will is arranged based on the design theoretical basis of design. The two winding concerning their relative angular position in continuous form. Those winding distribution functions can be written as follows: and main winding function and the auxiliary winding function and W as a summation of K and typically winding 5 sin ISM, and similarly for all harmonic 1, 3, 5, and similarly Ki auxiliary winding cos ISM. From this reference, the winding functions for such two-pole motor thus can be expressed as follows: omega j as a pi sm equal to half equal to 0 to pi and I alpha into d alpha, and minus 0 to pi sm and j alpha d alpha, where j equal to mw and AW main winding auxiliary winding. The two winding currents IMW and IITW can be adopted to obtain the stereo MF as follows: the MF SMT equal to omega MW phi sum IMW is a function of time plus IWA phi sum IAT into T auxiliary winding current, and the distribution factor can be commonly applied to assessing the contribution of the phase winding of the geometrical air gap magnetic as KD equal to cos H comma by 2 into Nk upon Nt cos K minus 1 H by minus sin H by 2 into Nk plus 1 upon Nt H sin H Ky, where K1 is carrying 1 to 3. And you can see how really the main winding is special MF for single phase 2 pole 24 slot and 3 winding arrangement model A and C with the same winding terms is petal MF distribution fundamental component harmonic of these, like for model 1, 2, 3, like. And this is the distribution of air gap MF, illustration of MF of 2 pole single phase 24 slot, comparison of MF percentage of their respective synchronized speed. These typically the decompose air gap MF propagate at their respective synchronized position for the two cases, and then the conceptual winding arrangement of the two induction motor, one for commercial and other new design motor for high efficiency. And these are winding arrangement for the 24 slot motor, old and new motors typically. And the major result of the two capacitor run from the experiment, and they are able to get a typically efficiency improvement order of 74.75% to around 80% efficiency for designing of the new design motor. So coming to conclusion, the stator windings of a commercial single phase capacitor run induction motor can be systematically arranged on the slot to improve the efficiency of all the possible operational conditions. The main design idea is to appropriately reduce the air gap backward MF such that the composite MF fluctuate in the desired forward direction can be minimized. Now coming to exercise and problems. So question is, what is the saturation factor of an induction single phase induction motor? The answer is the saturation factor in induction motor is a measure of how close the magnetic core is reaching in saturation point. It is expressed as the ratio of actual magnetic flux to the flux that would be present in core were saturated. Induction motor designer need to consider the saturation factor to ensure the motor operates within the acceptable limit. Excessive saturation can lead to increased losses, core losses, and reduce efficiency and undesirable effect on the motor performance. The question 2 is, what is the pull-out torque of single phase induction motor? Pull-out torque represents the maximum mechanical torque that the motor can develop without stalling or coming to a halt. It is a critical parameter in applications where the motor needs to overcome high loads or torque requirement. Now question 3, discuss the consideration involved in selection of distribution number of turns and wire size of auxiliary winding. The selection of distribution number of turns and wire size of the auxiliary winding in induction motor is a crucial aspect of the motor design process. The auxiliary winding, also known as the starting winding or starting coil, is also responsible for providing the initial torque to start the motor. Here are the consideration involved in making these selections. So first is the distribution of winding, like a special distribution or proper phasing, and second is the number of turns, like a starting torque and impedance matching, and third is the wire size, current carrying capacity, resistance, and space constraints. Like. Now coming to question 4, discuss what factor influence the relative amount of copper in the two winding of a capacitor start motor with particular rating. The different purposes of motor operation and their design involve consideration related to amount of copper use. Several factors influence the relative amount of copper in this winding, like operational requirement, current handling capacity, impedance matching, power factor, space constraint, and efficiency and performance. So question 5, what is the effect of oversaturation on an induction motor performance? A high saturation factor implies the magnetic core is operating near its saturation point, and designer may need to adjust the motor design or select the different material to optimize performance, and balancing the saturation factor with the other design consideration is crucial for achieving an efficient and reliable induction motor design. Now question 6, find the main dimensions of 450S230 375 watt single phase induction motor. Assume the required data. So NS equal to 125B is 1500, and in RPS it comes like 15 by 60, so 25 RS, and watt per RPS is 375 by 2015, 415 watt per RPM. Cos theta and cos phi equal to 16.75. So motor, now you can call it d square L Q upon it, NS into C0 and eta cos phi. So d square L equal to Q upon C0 NS. So from putting a value here, d square L comes 0.895 minus 10 to the power 3 meter cube. Separate dl, L upon tau taken 1. So it means L upon tau, L equal to tau, and tau is equal to pi dp, that is 0.785, and L equal to 0.785 d. So d square cube equal to, putting a value, it comes d equal to 0.1045 meter, L equal to, putting 0.785 equal to 0.082 meter. Now question 7, calculate the main dimension of 22 watt 230 volt 4 pole capacitor run single phase induction motor. The power factor and efficiency of this motor should not be less than 0.95 and 0.8 respectively. The value of aspect ratio should be considered so that the flux density in the back core and stator does not exceed 1.4 Tesla and 1.8 Tesla respectively. The number of stator slots should not be greater than 36. Calculate the number of turns required for main winding for above specification, and if permissible current density of main winding is 4 ampere per millimeter square, calculate the wire of main winding, stand wire gauge. The slot fill factor should not exceed 50%, including the insulation. Coming as a solution, watt per SPS is here 2200 by 25, 88 for watt 88. The C0 eta cos phi is 60.172 by floating the initial value double linearity to obtain y equal to 0.596x plus 7.6636. So d square L is P0 P divided by C0 eta cos phi, it comes 1.46 into 10 power minus 3. Assuming L upon tau 1, so L equal to 0.7853 d, and d square d cube is 0.783 equal to 1.4, and d from this d comes 0.123 millimeter, and L is 0.0966 meter, and WTS is putting where dimension it comes 3.35 millimeter, and the flux phi putting the value in this relation comes 5.25 Weber, and By is 1.4 Tesla. So from this DCS comes 19.38 millimeter, and for winding factor KW 0.8, so TM comes value 235, and turns per pole is 58.75, so 58 turns per pole, and stator slot per pole is 36 by 4, that is 9. And the winding factor calculation are slot 1 to 9, that is sine 8 by 9 into 90 and 9848. Similarly, slot 2 8. So all winding factors are total calculated 2.835. Similarly, it's calculated for all 1 to 9 and 4 to 6. So combined for each, it comes like typically comes as a 58 turns, and round of each comes 21, 17, 13, 7. Sum comes as a 58. So here the winding factors with these winding number of turns calculated 0.7957, and this is around 0.8, which goes to estimate value. So magnetizing current comes, main winding current comes from the calculation. This 12. Mains current comes 12.58, and taking current density 4 ampere. Area of conductor pi d by 4, so that is 3.145 millimeter square. Where the d comes 2 millimeter, 2.001 millimeter, and a slot, area of slot a copper divided by fill, putting value, it comes like 84.045 millimeter square. These are the references which are really used for developing this material, and thank you.